I love this kind of computer science videos. Just the theory and a blank sheet of paper. This is how you really use your imagination to understand computing. Well, absolutely. Reading is probably the closest we've got to telepathy. It's mentally stimulating to reconstruct the information in your own head and adapt it to your own situation. You should make more of this type of video. It's like watching ASMR and learning at the same time. Did you know I've actually got a second microphone set up here, and the reason I set it up was to capture the keyboard typing, but unfortunately the mic cable is just very sensitive and it's picking up a lot of noise coming from the computer, a lot of electromagnetic interference. So if you want electromagnetic interference ASMR, I can put that up. Just, ask. I'll make it. Interesting. Cheers from Portugal. Cheers, my man. Thank you from Russia. Keep going. Well done. Thank you. I will keep going. Interesting. Subscribed. Jump on in. The more the merrier. Thank you from India. All right. Yeah. Cheers. Hey, where are you guys viewing this from? Comment down below. Very helpful. Thanks. You are welcome. Can you give a practical example, specifically the pool way? So far, I've just been trying to avoid dynamic memory allocation as much as I can. If I must, then I reallocate double to reduce the times I need to reallocate. Okay, so recently I've been thinking about pedagogically sound tutorials. There are a lot of tutorials out there which are actually not tutorials. They're like light entertainment, and they just give you the facts. I could give you the facts. I could show you how I implemented this stuff. I've implemented it. I still need to iron out some details, but as we can see here, I've got some memory allocators which are, at least in my tests, performing better than Malik. But if I were to give these details, that would take away the benefit, really, of learning. My purpose is not to teach people exactly how to do what I did, but rather to teach the concepts so that you can extend. And I mean, if you really think about a memory allocation pool, you have a number of fixed size allocations. Every time you tell the system, the library, that you're requesting an allocation, it will give you the next available one. Do some internal bookkeeping. I think, not to sound rude, but really truly, it's a good exercise to think about from that concept, translating it into code. And if you're having trouble translating that into code, again, not meaning to sound rude, but it might be time to go back to the drawing board and refresh on the coding. Now, as for that second part, reallocating twice the size, that is a completely valid approach. You see, the point of dynamic memory allocation is it's bad, so you want to do it as little as possible. If you were to amortize out with a doubling strategy, it would amortize out to a constant factor. But then the difference between, well, first of all, reallocating a whole bunch of times is not as good as reallocating with double the size every time you need to. So that's an improvement. But then the constant factor that your reallocs amortize out to may be less than the constant factor that you would have implementing your own memory allocator. Actually, under the hood, I would be doing something like realloc, potentially even with a memory pool. Think of it as a hierarchy. The purpose of memory allocation, or really program design, is to be able to critically analyze how dynamic you actually need to be. I hope that makes sense. Anyway, doubling strategy, perfectly legit. And as of recording right now, we have another comment. Hey, thanks. Thank you. Deleting Reddit might make you feel empty or bored at first, but later on you realize how bad the platform was. 100%. And it's gotten worse, hasn't it? Here's what I've been doing recently. Anytime I'm waiting for the bus, it might be like a 10-minute wait, 15-minute wait, I open up my phone and do some random Google searches on topics, computer science topics that I want to learn. Even if it's just little Python modules or something, I find that more productive than Reddit. 100%. What do you guys do in your spare time? Let me know down below. Let's start a conversation. Hello. So on to today's topic, and that is low-level memory manipulations, bit manipulations. For the purposes of this topic, I'm going to just assume that we're dealing with 4-bit numbers, being unsigned integers. So let me just write out a random number. There are a few bit level operations we can perform. One of these is bitwise AND. That's just a single ampersand, a single AND. And this takes in two numbers as its input, and the output is analyzed sort of on a bit by bit level. And each bit will only be set if that corresponding bit position is set in both numbers. We also have the OR, and this will set the bit in the output if one of the bits is set. We also have exclusive OR, and this will set the bit if one but not both of the bits are set. So these are some examples. We also have the complement. So if I have the bitwise complement of the following number, okay. To add to this, we have some observations with AND and OR. What I want to really look at is the identity operation. So if I have some bit, it doesn't matter what it is, and I take its value and the bit 1. So we say, well, if x was 0, we take 0 and 1 is 0, and if x was 1, 1 and 1 is 1. And so another way to look at this is to say, well, 1 is the identity element under bitwise AND. Anything with 1 keeps it at itself. And likewise for OR, if we have 0, so again, x or 0. So if x was 0, 0 or 0 is still 0. But if x was 1, 0 or 1 would be 1. And so likewise, the identity under bitwise OR is the element 0. Now, why is this really useful? Well, let's say, for instance, we want to set bit 2 in x, and I'll make it really, really clear like that. I want to set bit 2. What I want to do is take a mask or a number such that when I perform bitwise OR with this input, the output is pretty much the same as originally, except that the second bit is set to 1. So everything else is unchanged. So I go bitwise. The identity operation with OR is 0, so I have 0, 0, 0, because I'm not setting the first two or the last element. And then I'll just put a 1, because anything OR with 1 is 1. And then likewise, let's say we want to clear bit 2 in the following number. This is just a, just a simple example. So I think just pretend this is a 1 or something. It doesn't matter at all. So I'm saying, what is an operation that I can do on this second bit such that no matter what its input is, its output is always 0? Well, one way to do this is I know that any number and 0 will always be 0. But then the question is, okay, well, what can I put in such that when I operate it and the other bits, they are unchanged? And again, that's the identity element for AND, which is 1. So here I have 0 and 1 is 0, unchanged. 1 and 1 is 1, unchanged, and so on. 1 and 1 is 1. Excellent. So then the next question is, how can we sort of construct these sorts of masks really, really quickly? I'll just go ahead and write it. So if I take the number 1, imagine that I want to have some output which is 0, 1, 0, 0. So the 1 gets shifted into bit 2, 0, 1, 2. In other words, I take that 1 and I shift it 2 bits up, because under the hood, this 1 is really the number 0, 0, 1. So imagine, shift that. I'm saying the same thing from a bunch of different angles. So what I could really do, if I were to generalize this operation of setting bit 2, I would say x is equal to x, or this operation here, this mask, which is that 1 shifted up by 2. Okay. How about this mask down here? I want a 1. When I say this, yeah, I mean this should really be 1 for this example specifically here, but we'll go with this. Now, if I do this, I shift it up by 2, I know that I'll get, whoops, tripping myself up. I know that I'll get this number here. And now what I want to do is invert all the bits. So what I'll do is take the result and then invert it. This is a mask which would clear. Yeah, my notation here is a bit off, but it would clear the bit that I want it to clear. So we could say, for instance, x equals x and not the following. In these cases, I sort of messed my notation up. The offset, it's wow, not even bit 3. Oh my goodness. Oh no. Yeah, bit 1. But such surface level details, this is not worth worrying about. There's another thing that I can do, and that is to look at this number, 0001. If I were to evaluate that in binary, that has a value of 1. Whereas if I were to evaluate this number in binary, that has a position of 1, 2, 4. That has a value of 4. And so it turns out that every time we shift to the left, we shift a number up, we increase its magnitude. Every time we do that, we are doubling its value. So if you're working in powers of 2, if your problem can be phrased in powers of 2, then this is a really quick way to double, because all of these bit level operations are executed very quickly in assembly. And likewise, if we had a number and we were to shift it down by 1, well, yeah, we shift it. But if we were to look at the values in binary, we can see that shifting down will halve the value. So again, if you're dealing with numbers and everything's powers of 2, then it's really easy to quickly apply these transformations. Let's look at some practical applications of this. So recently I was working with sort of a pool, well, not a pool, a tree, where we have, for instance, 16, let's go with 16 bits of memory just for this example, and we want to recursively subdivide this. just like that. Now, all of these are actually referring to partitions of the original memory allocation. So if I were to write the address just as a number, as an offset, this memory allocation covers everything. Its offset is the beginning of the block. Same thing actually for all of these cases. But then if we go down here, this case, again, it's the same memory allocation, but it's a different offset within that block. And so on and so on. You can fill in the rest. But we have a problem. And the problem is, given that I have allocated the following block, well, this location here should be okay. This location down below, its child, we want to somehow indicate that that's been allocated. We want to somehow indicate that this one's been allocated and that this block has been allocated. Because that beginning location here, this bit, this allocation is taken up. So this might be a poor example because it's pretty straightforward, but let's look at this one over here. In the previous video, I was saying that these sorts of memory addresses can be deterministically calculated, but what does that even mean? Well, for each of these, let's say we have a level. So I'll call this level 0, level 1, level 2, level 3, I guess. And then within the level, each block would have an offset. So I'll call this an offset of 0, an offset of 1, not 2, an offset of 2, 3. Okay, so let's look at the left child of this allocation. Well, the left child will be, its offset will be 0, 1, 2, 3, 4. And the right child will be an offset of 5. Its parent will be an offset of 0, 1. And this parent will be an offset of 0. What pattern do you notice? That's right. If we know the offset of a node, then to get its child, we would shift that up by 1. We would double it, and that gives us the left child. Then the left child address plus 1 is the right child. If we were to go back, then we would take that offset, whoops, wrong direction, shift it down by 1, halve it, and that gives the offset of the parent. And this still works, because if we were to take 1 and shift it down by 1, again, everything shifts down, right? So 0, 0, 0. Then what are we going to put in the left spot? Fill it with 0. It's nothing after all. So we can repeatedly do this, and this will deterministically calculate the offsets of the children and parents within each level of the hierarchy. Now I'll leave it as an exercise to you to fill in any other implementation details. Here's another example. Let's say that I want to keep a Boolean flag for every block at every level to indicate whether it's free or not. This would be a lot. 1 block, 2 blocks, 4 blocks, 8 blocks. That's 15 blocks. And you can imagine as the memory allocations get beyond 16 bytes, that's an incredible number of blocks. But what we could do instead is we could have an integer for every level and so on. I don't know why I numbered them with letters, but what we'll be doing is each of these integers will have a certain number of bits, and the position, the bit position, corresponds to the offset within that block, within that level, and the value of that bit, whether it's a 0 or 1, corresponds to whether that block is allocated or free. So we can then quickly mark blocks as allocated or free, just with bit level operations. We can quickly check if a given offset is free or not. It's much faster, and it saves space, because If we were to allocate this space as a bunch of booleans, well, under the hood, the compiler would promote those booleans to larger storage variables. We can't have individual bits. If we're lucky, it optimizes it, but if we know what the optimization is, why not do it ourselves? Okay, so that was that example. Another example is if we are using integers to represent more information than just a number. For instance, a color. Let's say we have a 32-bit integer and we're using it to store RGBA colors. Each channel is a character, is a byte, is a value between 0 and 255. So we would have 1 byte for our red, 1 byte for our blue, G, you know what I mean, and so on and so on. So here I've implemented a raycaster, but the raycaster sort of does everything on the CPU. So it goes through, it does its raycasting, it writes those numbers to the CPU, to an array, and then it uploads that to the GPU, and that gets displayed. Let me just give it a go. Here we are. Here's our raycaster. This is just the standard raycaster tutorial, but implemented with a CPU frame buffer. Anyway, as you can see, it's going fast. It's going too fast. But how am I getting these colors into the numbers? Well, if we just close this down and have a look at this operation, I'm basically using bit shifts. So I'm saying, hey, in order to transform an RGB value in, we could take the red value and promote it by some offset, take the green value, promote it by some offset, just like that. And this is actually packing those bytes together into the result. So there we go, magic. So today we looked at low-level, bit-level operations, some things we can do with them, some examples. But yeah, hopefully you enjoyed that. Hopefully you got something out of it. Hope your day's going well, and I will see you again soon. Bye.